is basically a subfield of AI, which focuses on the interaction between computers and humans and human languages. The goal is to enable machines to understand, interpret, and generate human language. When talking about understanding, interpreting, and generating human language, one of the recent examples that probably all of you had experience with is ChatGPT, which can understand you, which can interpret your prompts to a very good extent, and also it can generate very decent responses. So, however, NLP utilizes various methods from different subfields. For instance, from computational linguistic, which focuses on the linguistic aspect of text and how text is represented, and what are the rules that are what are the linguistic rules that are governing a text. By understanding and knowing what are these rules and how a text is represented, one can write rules or the right programs for computer to computationally understand the text. Also, we have many methods from machine learning. Machine learning in NLP, specifically deep learning, has been the dominant approach in the past decade. Also, we need knowledge from semantic theory, which deals with the meaning of the words and how the meaning of a word is represented. By having all of these methods at our disposal, we can process and analyze large amount of unstructured textual data. Remember, we are needing natural language processing to process unstructured data. If we have a structured data like we have in relational databases, we don't need language processing. Talking about unstructured data, one of the instances of the unstructured data is medical text and, for instance, clinical report. So here we can talk about the applications of NLP in medicine. It has many applications. So far, you have learned about the applications of machine vision and image processing in medicine. However, we are taking a break this session from image processing and focusing with a shallow focus on natural language processing. We can use it for information extraction from clinical reports. Clinical reports often contain many mentions of drugs and treatment modalities and other information. We can extract such information to better provide information to medical practitioners. We can use this for clinical trial matching. What does it mean? It means that based on the patient medical history, which is recorded in form of clinical text, we can match a patient to proper clinical trial that matches their medical history, family history, so on and so forth. We can use it for patient risk stratification. Based on the patient history, which is again reported in form of text, which patients are more at risk for specific diseases. And we can use this for medical coding, pharmacovigilance, and adverse event monitoring, and automated report generation. All of these are the applications of NLP in medicine. So, but let's review some common tasks with the focus for medical notes and clinical text. We can classify clinical text, for instance, classifying notes for medical specialty. Suppose we have a set of notes, many notes. We don't know which note is related to which specialty. We can provide these notes to NLP based classifier, and this can partition our clinical notes. Or we can have named entity recognition. Named entity recognition is one of the most important tasks in NLP. It deals with classifying entities into predetermined categories. For instance, here, the two categories that I'm interested in is the test that was performed and the disease that was detected. So here I'm focusing on the mention of tests and diseases. Chest CT was negative for pulmonary embolism. So here are my two entities. Note that we don't have a verb in name entities. Named entities, as the name suggests, named. It deals with nouns and names. Then once these entities are detected and are recognized, we can focus on co-reference resolution, which is basically finding all mentions of these entities that refer to the same entity. Why? Because an entity in a clinical report might appear several times in different forms, but by different means. Here, for instance, the patient was found, this is a piece of clinical report, the patient was found to have chronic obstructive pulmonary disease. Okay, the patient continued to become weaker, and it was clear that her COPD was end stage. Okay, so we have an acronym COPD here, COPD and chronic obstructive pulmonary disease. They're referring to the same entity. So the purpose of co-reference resolution is basically to disambiguate between these multiple entity mentions. Once all of these entities are extracted, the entities of interest are extracted and their references are resolved, we can focus on extracting relations between these entities. Which comes to the relation extraction. Relation extraction is basically the task of detecting semantic relationships between entities. Okay. Again, these entities that we have extracted, here I have two entities, a CT and a disease, a finding, okay, was performed, which revealed the presence of a disease, okay? So there is a relation between that kind of test that was done and the disease. The relation is a finding relation, okay? And depending on the task, we can define different relation types. It's up to us. Depending on the task, we can define different name entities. For instance, another name entity that can be defined is the dose of a drug. Okay. For instance, this drug was prescribed with this much milligram, this much twice a day, or once a day. With how many frequency, with how much frequency. And then once these informations are extracted, these information can be used in downstream tasks, for instance, to detect the outcome of treatment and find the relation between the outcome of treatment and a specific dose of a drug, okay? So yes, a wealth of information is buried in these clinical notes. But natural language processing pipeline often has several important stages. The pipeline starts with receiving the raw text, and then the first step, usually it's not always the case, but in the most of cases, usually the first step is in an NLP pipeline is the tokenization, which basically refers to breaking a text into smaller units, or what we call tokens. For instance, here, this is the raw text. The chest CT was negative for pulmonary embolism, and we want to break down this text to smaller units. So these are smaller units. Our chest CT was negative for pulmonary and embolism. So each of these, each token is a meaningful unit. Do I mean by this? I mean, if we further break down this chest, or we have something like chet, which is not a meaningful unit. If we break this we have was, if we have wa, okay? Or if we break down nega and we don't have tiv, it's not a meaningful unit. But there are certain cases that, for instance, if we further break down a token, we might have meaningful units. Okay, for instance, many of the adjectives. Okay, so for instance, warmly. If we consider the adjective warmly, warmly consists of warm and suffix ly. Okay, so warm is a meaningful unit, but ly is not a meaningful unit. Okay, so but overall, these tokens are meaningful units. But the point is tokenization. If you look at this example, the tokenization was done at these blank spaces. Okay, this was a very easy case for a tokenizer. The tokenization at the blank spaces, but it's not always the case, and it's not always as simple as breaking at the spaces. Why? Because we might have hyphenated terms, we might have commas in the text or parentheses. An example is here. Okay, the patient was presented with a hyphenated term here, disease, and then I have a parentheses, then an acronym and the close parentheses, and was prescribed proton hyphen pump inhibitors. Okay, so here I have two mentions of a hyphenated term. So the question is, do we consider this hyphenated term, the whole term, as a single token, or we consider it as three tokens, gastro and the hyphen, and then or proton or a hyphen and the next token. Okay, so these are design questions. So, but overall, since gastro is a meaningful term, it usually is this is the case that we break at this hyphenated term, and also we don't consider this whole strings of characters as a single term. We consider it as a single token. We consider open parentheses as a single token, GRD as a single token, and close parentheses as a single token. So, but these are the design questions, and I wanted to turn your attention to how different difficulties and complexities in a text can affect design choices in the tokenization. The next step is part of speech tagging. It's a very common module in often in a NLP pipeline. It often comes after the tokenizer. Why? Because it is applied to each of these tokens. We are assigning to each of these tokens their syntactic category. Okay. And these syntactic categories are assigned based on the contribution of a word and a word to the meaning of the sentence or the phrase that contains these tokens. Most of common part of speech are nouns, verbs, adjective, pronouns, prepositions. We learned most of these in primary school, but it's good to review this. So these syntactic category can provide very valuable information for other downstream tasks, the tasks that require an understanding of the grammatical structure of the sentence. We usually assign a close set of tags to these tokens. For instance, a noun is represented by NN, chest CT, NN. VBD is the past tense. JJ refers to the adjective. IN refers to a preposition. Pulmonary, again, an adjective, an embolism, and noun. Okay, so the question: what is the use of these part of speech tags? For instance, it can be used for named entity recognition. Named entities are nouns or noun phrases, right? So I'm not interested in the was. Okay, in was, because it's a verb. I know that this is a verb. I can prune this and basically cut this in my as a potential token for my named entity. So I can focus on noun phrases, which is a collection of nouns. Or here I have another noun phrase, pulmonary embolism. So my candidates would be chest CT and pulmonary embolism, just like I had in the slide that I introduced the name entities. And another common module or common pre-processing in an NLP pipeline is dependency parsing. What is dependency parsing? Dependency parsing and basically a dependency grammar postulates that the syntactic structure of a sentence is represented by relation between pairs of words. These relations are syntactic relations which exist between a governor here and a dependent. A governor, or what we also call head. We have relations from a head to a dependent with a specific type. These relations are asymmetric relations, and again, these are typed. By looking at these relations, we can extract many useful information, and we can use it, for instance, for downstream tasks such as relation extraction or event extraction. For instance, suppose we have a pharmacovigilance application, and we want to identify the adverse events for the drugs. What are the side effects of a drug? What are the toxicities associated with the treatment? What we can do, we are interested in finding the events that has happened somewhere in the text, okay? Because these for instance, adverse events are reported again as an event. So one of the most important or two most important relations that a dependency parse can provide us is the subject verb object relations. So subject here is lenvima, here is the subject. It did something on what? On the pain. Okay, so lenvima caused something, right? So the question, when we are looking at this subject verb object triples or SVO triples, as we commonly say, we are interested to see who did what to whom. Okay, so lenvima caused something. By only looking at all of the instances that a drug is the subject of the sentence, we can quickly extract many good information and valuable information, even without training any model. So the theme of my talk is, until now, is to a little bit distance ourselves from neural network and deep learning, and really appreciate the structure of the language and how knowing about the structure of language can help us to extract many valuable information. So these dependency parsers are available in most of current NLP pipelines, NLP libraries, which I would introduce some of them in the next slides. So some of the NLP libraries that are freely available to us, I'm mentioning here. One is Gated. This is my preferred NLP tool. It provides a user interface that you can look at different annotations and different features and extract different features from text. It has a modular design. It is Java based, so you can write regular expressions over text and over these annotation types, and extract different information. Other Other libraries also include Spacey and Stanza. Stanza has been recently introduced, maybe in the past 1.5 years or 2 years, compared to Spacey and Gate. Among all of these, Gate is the oldest one, which is still being introduced. New versions are introduced for all of these softwares. But it depends. It depends on your application. It depends on the backbone of your model, whether it's Python or whether it's Java. But the point is, recent versions of Gate, they have provided Python wrappers also for this. So you can use all of these for your purposes and for your task. So let's now talk about neural NLP. Up until now, when I was talking about tokenization, part of speech tagging and dependency parsing, these we're dealing with these in a rule-based point of view. Okay, so these tasks. They really don't require any deep learning. However, we can use deep learning to further improve the accuracy and the performance of these tasks. So deep learning has been the dominant approach for most of the AI models, including NLP, in the past decade. Just like other tasks, for instance, the task of segmentation in image processing. At the end, you are defining the task of segmentation as a classification task. For instance, to classify whether each pixel belongs to a segment or not, or each voxel belongs to a segment or not. Okay, so at the end, most of these machine learning tasks and most of these machine vision tasks or NLP tasks, they are modeled as classification tasks, and then a neural model is trained end to end. What do we mean? It means that we are only providing the raw input or the input with minor pre-processing to the system, and the system tries to extract features, meaningful features that can be used for downstream tasks and can solve downstream tasks. And basically, the system is trying to extract some sort of knowledge from its input data. A major distinction between NLP, neural NLP, and machine vision is how we are representing our inputs. Note that images, they themselves are represented by numbers. Each pixel is represented by a number between 0 and 255. Okay, so we don't need usually any sort of encoding for an image. Yes, sometimes we do transformations on an image, we do scaling on an image, but to give an image to a machine learning model or a neural model, we usually don't need any encoding. However, this is not the case for tokens, because tokens are in form of a string and are in form of text. And first, we need to convert these tokens into numerical format, and then use the encoded version or that proxy as a means to represent our inputs. So we are representing tokens in vector spaces, and we are calling these representation word embeddings. But let's first have a brief review of what happened in the past 20 years. So the first neural language models was introduced by Joshua Bengio in 2003. Then these neural language models, we had improvements for these models with multitask learning paradigms. Then around 2013, we had word2vec as one of the first word embeddings. We were pre-trained word embeddings, and then the layer later we had glove. Then throughout 2013 until 2015, we had different models developed for neural NLP. In 2017, actually, this is not a correct number. In 2017, we had transformers, which basically used the attention mechanism, and then in 2018 we had pre-trained models such as Elmo, BERT, and so on and so forth. So let's talk about word embeddings. So word embedding is basically a vector representation for a token and for a term. Okay, so we are representing each term. Okay, suppose you have opened a dictionary. So you have a vocabulary, a vocabulary of all of the terms that we have, or a majority of the terms that we have in a language. Okay. The purpose of word embedding is to basically to assign a vector representation to each of these terms in our vocabulary. So how these vectors are obtained, this requires a dedicated tutorial. But there are some approaches, for instance, context-based approaches like word2vec and glove that looks at the context of words and obtains a representation for each term in the vocabulary. But this is not the topic of discussion at the moment. So each term here, for instance, this, he, these terms, these are the sort of all terms that we have in our vocabulary. This, he, CT, cancer analysis, brachy, so patient, MRI. So there are many terms in our vocabulary. So we are representing each term. So first we are making a correspondence between a term and an index. Okay. So this is an arbitrary indexing. So we say this, the term this would be at index 0, and this is its vector representation. We could have put this representation in another row. It doesn't matter. It's an arbitrary assignment here. Then CT is it has row number 2. And by to follow Python syntax, I'm using indexing from 0. Then I have cancer analysis brachy at the last row, and the cardinality. So this represents the cardinality of the set of all of the terms in my vocabulary. Okay, so under certain conditions, these representations, so these are vector representations. You can measure the similarity and measure the closeness of these vector representations in a vector space. Okay, so under certain conditions, often the terms that are related to one another, they are often closer to each other. For instance, CT, MRI, these terms would be closer in the vector space together compared to, for instance, to a drug. Okay, so drug, the terms that are describing a drug, they would be closer to one another. The terms that are describing different types of cancer, they would be closer to one another. So these word embeddings, these pre-trained word embeddings, they are available for download, usually in TXT file format or other formats. But it's very common to have them in TXT format, and in our notebook and in our tutorials we would have a look at one of these vector presentations. So once we have downloaded all of these vector representations and these word embeddings, we can load them in what we call an embedding matrix. Again, an embedding matrix it's basically a correspondence between an index and and basically a term. So we are keeping this conversion, this token to index conversion to later convert these tokens, the tokens that we have at our input, to their corresponding indices, and then retrieve the embedding vectors at those indices. So let's talk about one of the neural layers that we have for text processing. So these word embeddings that I talked about, our input is converted to a set of or sequence of word embeddings, and then the sequence of word embeddings can be provided to a neural layer for further processing and for training purposes. So one of the very popular neural layers is CNN. CNN were first developed for image data. However, in 2014, they were also applied for text classification. The idea of applying CNN for text classification is to see the textual input as a matrix like this. Suppose you have a very short text like this. Labetalol. This labetalol is a drug for blood pressure. Is not effective. So suppose this is the embedding from labetalol. I have retrieved this embedding from somewhere in this embedding matrix. Then I have retrieved it again from the embedding matrix, not an effective. I have retrieved these embeddings. I have stacked these embeddings on top of one another to form a matrix like X. Okay, so the idea is to just see this textual input as a matrix, just like an image. Okay, so now we can assume that this is an image. However, the difference of applying CNN to text compared to the image is that on images we could have filters that only overlaps with part of the area of part of the image. However, for text, okay, since as I mentioned in the second slide, since the smaller unit of the text is token, we cannot just apply the filter to half of the token. Okay, the idea of applying these transformation to half of this representation is explored in transformers, in multi-head attentions and transformers, which is the topic of discussion for the next week. However, here for the CNN, for text classification, we are applying the filter over the whole embedding of a token. Okay, so we would have so the filter size needs to be same as the embedding size, which I represent here with D, and it has a length. Okay, so here I have a size and I have a length, and we are sliding just like image processing, CNN for image processing. We are sliding this filter and we are convoluting this filter on this textual input or over this matrix. So first we are applying this filter by convolution over this area, over this bigram, okay, over the labetalol is. So right now, because the length of our filter is 2, one can argue that it captures bigrams in a textual input. We can have filters of different sizes. For instance, 1, it would be unigrams, 2 bigrams, 3 trigrams, and so on and so forth. So a trigram filter, a filter with a length of 3, it would capture trigrams. Okay, patterns of 3 consecutive tokens. For instance, labetalol is not. Nevertheless, we are sliding this filter over our textual input, which results in a feature map. This feature map then can be used for our classification. Just like CNN for image data, we are not we don't have only one filter. We have multiple filters, maybe 10 or 20 filters of different length. Okay, so we would talk about CNN for text classification in our notebook. The next type of neural layer that can be used for text processing and NLP is a recurrent layer. Note that the text is a sequence of tokens. Okay, so it's a sequence. Okay, so a neural layer needs to accommodate this fact that yes, there is an order between these tokens, and these tokens are coming in sequence. Okay, so a recurrent layer can process sequences. So what is the difference between a recurrent layer and a feed-forward network? The feed-forward network only has one vector as its input. However, a recurrent layer has multiple vectors as its input. Here, in this case, capital T vectors as its input. Which basically T is the length of the sentence or the number of tokens here. Once applied to this sequence of inputs or the sequence of the basically token embeddings or word embeddings, it provides the hidden representation. So how a recurrent net or RNN works? It basically, you're providing the input at the current time step or at the current position, okay? And it also takes into account the hidden representation from the previous time step, okay? So, which we can unfold throughout the time. So, hidden representation, this hidden representation, HT, the hidden representation at the current position or at the current time step, is a function of the current input and the previous hidden representation, the hidden representation corresponding to the previous time step. So, and we are usually applying a function over this. We can apply, for instance, a function hyperbolic tangent. Okay, so this function is basically characterized by two trainable parameters, W and W tiled. So note that since we want to map xt and ht minus 1 to a ht. Okay, so the result of this process or this summation, multiplication and summation should be in dh dimension here. Okay, so the dimensions of ht is dh. I'm representing it with dh. Okay, so it means that we need to map xt into dh. So we are using a mapping or projection from the d of input, the input dimensions, to dh, and we are keeping the last hidden representation or the previous hidden representation in the same space. Okay, so what does this hidden representation represent actually? So HT basically is a representation of the sequence up to that position. For instance, H2 holds all of the information that we have from all of the inputs that we had so far. So if you look at this, look at this relation here or this equation here and how HT is represented. Here we have here at HT relate is dependent on HT minus 1. So H2 is dependent on H1, and H1 is basically dependent on X1 and H0. Okay, and again, if you are going down here, it is dependent. Capital T is dependent on, is a function of XT and HT minus 1, again, which goes back through time. Okay, so actually here we are having some sort of Markovian assumption. Why the first order Markovian assumption? Because HT is only dependent on the current input and what we had in the previous time step. So here the last hidden representation can be seen as a representation for the whole sequence and can be used for instance for document classification for instance to classify what is the label or type of for instance current medical note. Okay, let's implement. Any questions so far?
Yes, there has been a question on the chat. It has been partly answered by our two mentors, but maybe you can come back briefly on the embeddings part. So there has been some questions like, what are these numbers? And actually, you mentioned that we need to map the words to indexes because
Yes.
the neural networks, they take as input numerical values. But like, what are these embeddings? Why should we choose one embedding strategy for another, or can you go back to explaining why we need these embeddings?
So, okay, the question of why we need this embedding, because we want to represent them in a numerical format. So somehow we have to convert these tokens into numbers. Let me go back to my slides again. So the point is somehow we need to represent a token in a numerical format. Okay, so before the dawn of these pre-trained word embeddings like word to vec or glove, I will talk about how these are briefly how these are obtained. But before we had word embedding or glove, we constructed an embedding matrix like this, but these numbers were randomly initialized. So we had a vocabulary. Okay, what is a vocabulary? If you open up the dictionary, we have a and so on until zebra at the end. Okay, so we have a set of terms or vocabulary in a language. Okay, so we can represent each term in this language by numerical representation. Before this word to vec or glove, these values were randomly initialized and they were trained as part of the neural net. Okay, as part of the parameters in the neural net. So it's not different. These randomly initialized parameters, they are not different than compared to for instance the weights of a CNN layer that we are randomly initializing. Just like there are numerical values and they are randomly initialized and then learned with respect to a downstream task. These can also be randomly initialized. These numbers can be random and then trained with the downstream task. However, it's better to start from better position in our parameter space. Okay, it would be better to start with better values for these numbers, not from totally randomly initialized state, but from a better state. So this to serve this purpose, we're using word to vec or glove. Okay, so what are word to vec or glove? Basically, word to vec and glove are obtained by a unsupervised approach. Okay, you apply word to vec and glove model. They are also neural based, but again, the details are not important here. They are neural based, and I can refer you to proper readings on this. But these are unsupervised models. They're applied to large corpora of text. Okay, suppose you have gathered all of the Wikipedia or all of the content on the web, and then you are looking at a token and its surrounding. Okay, for instance, for word to vec or glove. So you're looking at a token and its context. So then you say, okay, based on this context, what is this token that I'm looking at? So you are masking, for instance, masking your token in the middle, and then you say, okay, I have this context. Can you predict what was the actual word here? Because in linguistic theory, there are certain theories about how we can about context and how the context affects the meaning of a word. Okay, so there is a very famous that I will talk. There is a very famous quote that I would have in my next week's presentation that talks about you shall know and you shall know a word by the context that it carries. Okay, so these word embeddings, they can be randomly initialized. If you don't have any word to record graph, suppose you have a language, or you have a language that came into existence yesterday, and you don't have any available word embedding for this language. Okay, so you're randomly initializing the embedding matrix, and then you're letting it through the downstream task. You're updating it through the downstream task, or you're initializing it with word-to-vec or GLOF, and then again you can fine-tune it to the downstream task. But I can refer you to proper literature on this. Any other questions?
I think that answers the question, but maybe since the question was first about the columns, can you touch like very briefly on how do you define this D, like the?
Okay, that's a very interesting question. So, the point is, so these are called dense vector representation. So when we're talking about dense vector representation, it is in contrast with traditional vector representations that we had for text maybe 20 years ago. Okay, that the size of the vocabulary basically defined the number of dimensions. Okay, so if you had 10,000 words or terms in your vocabulary, you had a 10,000 long vector. Okay. And actually, those dimensions meant something. Why? Because each dimension corresponded to a term in the vocabulary. However, here we have dense vector representations, okay, which are usually in the magnitude of 100 or 200 or at most 1,024 dimensions. So these are dense vector representation, in contrast to sparse vector representation that we had 20 years ago. Okay, so one cannot say what this dimension explicitly say what this dimension corresponds to, or what language feature correspond to. So if you ask me, okay, what does this 0.9 mean for dense vector representation, I can only speculate that it corresponds to some language features, or it implicitly this or a collection of these dimensions that are implicitly capturing some language features. Okay, but one cannot say that explicitly what does they mean. Okay, and basically that has been an active area of research of analyzing and interpreting these representations.
Thank you so much, Parsa. I think you can go ahead with the implementation.
Okay, so let's talk about implementation. So let me first share this notebook that I have in the chat with you all. Copy link. Done. So I'm sharing. Okay. Okay, I shared the link to this notebook that I have. Okay, so I'm partitioning this notebook in two major parts. So I want to talk about the stanza library. Sorry, let me have a sip of my coffee. Okay. So, I have to. Okay, let me. I have to make it public. Apparently, anyone with the link. Okay, copy link. Okay, I'm giving you another link. So I gave you another link. This is public. You don't need to request any permission here. So here I'm partitioning this tutorial this notebook in two parts. One language pre-processing using Stanza. This is a very lightweight. Notebook for how we can use this Stanza. You can use Stanza for doing pre-processing, for doing the tokenization, part of speech tagging, and dependency parsing. Okay, so we install a Stanza like this on Colab. Stanza is not installed by default. We can install it like this: pip install Stanza. Okay, remember to put this exclamation mark if you want to interpret this as a Linux command. Then once this is installed, I'm going to import Stanza, and once the Stanza is imported, I'm going to make a pipeline. I'm explicitly saying that this pipeline is for English language processing. It also includes modules for French, for Persian, Arabic, German, and most of these languages. So what are the stages in this pipeline? First, I'm doing a tokenization. Then I'm doing a multi-word tokenization. Okay, so I can talk about this. What is the multi-word tokenization later? But this is not the topic of interest at the moment. I can do part of speech tagging. I can do the lemmatization. So, for instance, what is lemmatization? Suppose you have vent. Okay, you have the word vent. The lemma of vent is go. Okay, so you can convert each word or each token into its base form, and then you can do part-of-speech tagging. So this pipeline comprises these different stages. So then I can present a document to this pipeline. So let's look at this document. What is this document? The document says patient presented with symptoms consistent with cancer, including unexplained weight loss, fatigue, and persistent pain. Further evaluation revealed a mass in the affected area, along with abnormal laboratory results indicating potential malignancy. Immediate referral to an oncologist for further diagnostic tests, and treatment planning is recommended. Okay, so here I have 3 sentences. So the interesting point of Stanza is that all of these the output of the pipeline is in form of object that one can iterate over. Okay, so this process text has many sentences, so we can iterate over the sentences. We can say for sentences in a sentence in the process.sentences, it returns all of these sentences in the process text. And then we can iterate over the words of this sentence as tokens, and then look at the information that is provided for us. Okay, so I'm making an instance. I'm importing Stanza. I'm making an instance of this pipeline using this. Okay, so then it would give a summary of what are these steps that the procedures that we have here. Okay, then I want to go over this text and see what is the structure of this text. So this is the first sentence. These are the tokens. Patient presented with symptoms consistent with cancer, comma, including unexplained weight loss. Okay, here after the token, so I'm printing the token ID. After it, I have the part of speech associated with this patient. Okay, so patient NN. So basically NN is the noun, verb, preposition. Symptoms is the plural noun. Consistent is the adjective. With is a preposition. Again, cancer is a noun. Then I have punctuation, which has a punctuation part of speech. I have a verb drawn in drawn form. Unexplained is again an adjective. Weight, loss, so on and so forth. Okay. So further, I have again I have another adjective. Okay, evaluation, revealed. So you can see, and you can actually look at the places. For instance, you have nouns or you have verbs. If you are interested in events, you are looking at verbs. If you are interested in, let me zoom in a little bit. And if you are interested in for instance, named entities, you're looking at, you will look at nouns. Okay. And you also here afterward, I have the token head. So in the dependency parts, if you remember, I had a head and I had a dependent. Okay. So I'm saying here, patient, the head, the ID, the ID of the head for the patient for the dependency relation is presented. Okay. Okay. So, and the dependency type is subject. Here, the dependency type is a conjunction. Dependency type is a compound. Why? Because it's weight loss. Okay, weight is in compound relation with loss. Okay, so we can look at different dependency relation and understand how you can utilize different dependency relations for your application. So this here, until right now, there's no deep learning. There's no deep learning used. Actually, so yes, I shouldn't say there's no deep learning used, because the backbone of for instance, this dependency parser is a neural dependency parser. But right now, these are annotations. These are textual features that I have extracted, and I can use it for rule-based system that I don't need to develop any deep learning pipeline. If you don't have annotated data, if your data set is of a small size, you can use good old-fashioned rule-based systems that are strong contenders right now, even right now, for compared to the deep learning systems. So now let's do neural text classification. For this purpose, I'm loading the pre-trained word embeddings. The pre-trained word embeddings that I want to load is Graph word vectors. This came out from Stanford, from Jeffrey Pennington, Richard Sacher, and Chris D. Manning. I strongly suggest all of you that are interested in NLP and deep learning in NLP to take a look at Dr. Manning's lectures on deep learning for NLP that are available online on YouTube. He's a rock star in NLP, in computational linguistics, and also in neural NLP. Nevertheless, you can download these pre-trained word embedding or word vectors, and you can look at the description for each of the set of these word vectors. For instance, this says this set of word embedding was trained on Wikipedia until 2014 and Gigavolt 5. It includes it was trained on 6 billion tokens. The vocabulary size is 400,000, and it is uncased. What do we mean by uncased? We mean that we have ignored the upper cases. So all of the tokens in this, all of the terms in this vocabulary are in lowercase. However, when it is cased, so it would increase the number of terms in the vocabulary, but you would have a different representation. For instance, for a cat that is coming at the beginning of the sentence, or a cat that is coming at the end of the sentence. So you can download each of these that are provided in zip format and in different sizes, 50 dimensions, 100 dimensions, 200, and 300. Okay, so here I'm downloading one of those with this command. wget this file, and then I'm unzipping it because it's about 800 megabytes. I already downloaded it. So, but I want to look at what it looks like Okay, so this is how it looks like. So by this head command of a text file, it's a Linux command that you can look at large files. You don't need to open for instance, a file that has the size of the file is, for instance, 1 gigabyte. You only want to see what this file and how this file looks like. Okay, so I'm only looking at the first few lines of this file. So you see, I have a term de, and I have a bunch of numbers, a bunch of representations for this term, and I have 100 numbers in the first row separated by blank space. Then I have comma, again 100 numbers, dot 100 numbers, and of, to, and, in, and so on. Each of these are represented by a vector in 100 dimension. Okay, so now that we have this text file, let's load these embeddings. And first, I'm going to store these embeddings in a dictionary. Okay, so I'm having a dictionary called word embeddings. The key to this dictionary, this Python dictionary, would be the token, the term itself, for instance, the. Okay, and then the value, it would be the actual vector. Okay, so here I'm saying for each of these terms, go over this. Also open first open the file, then go line by line, then split by the space. You can also split it like this, but if you don't provide any argument to this split function, it would split at the spaces. Okay, so the term would be at the 0 position, and the rest from 1 to the end would be the values. Okay, so here I would convert this to a tensor, because if you remember in my deep learning fundamental tutorial, everything that goes inside the neural network, a PyTorch neural network, needs to be in form of a tensor. Okay, so here I have a torch tensor. I'm having this vector in tensor format. Then I'm assigning that vector to the as a value of that dictionary. Okay. Then for the demonstration purposes, I'm saying the word embedding for the term scan, for instance, it would be the word embedding of scan. So you can provide the term and get the vector representation. Okay, you can provide a and get the vector representation. Then we have the vocab size. Okay, the number. What is the number of different terms? The vocab size should be 400,000. So let me just in here have vocab size equals to size. Okay, and the embedding dimension, if you remember, it was 100. Okay, then once I have loaded this, I'm constructing an embedding matrix. Okay, right now I have a term and its corresponding vector. I want to have that embedding matrix that I showed you before. I want to have an association between an index and a vector. Okay, so I would initialize an embedding matrix, an all zero embedding matrix with 400 for this vocab size and embedding D. Okay, remember it was the number of rows was the vocabulary size. Okay, and then I would keep track of this mapping for these terms. We'll look at some of these terms. Okay, so let's run this first. It imports torch because I need torch to make it and convert it to in tensor format. Then once it loads all of these word embeddings, it would print the word embedding corresponding to the term scan. It would take a little bit of time because it is 400,000 terms that it's trying to load from the file. Okay, so right now it executed this print statement. The word embedding for the term scan is this tensor. Okay, 100 dimensions. So the vocab size is 400,000. The embedding size was 100, and then Let me quickly take a look at this token to index. Okay, so let's have another code. So for instance, this token to index, which is responsible for mapping a token to to its corresponding index. Again, this mapping is arbitrary. Okay, so let's for instance have is. So the word embedding for is at the row number 14. Or let's have another one. Let's see CT, whether CT is in this. Yes, CT, the term CT is in row 16,909. Okay, let's have another one. Maybe hospital. Okay, it is at this. So we have this this mapping. So whenever in our text we have hospital, we would assign 726 instead of having hospital and passing a hospital to our network. Then when we pass 726 to this embedding layer, it would retrieve the corresponding word embedding. Okay, so I want to work with I want to do a text classification task. Okay, so I just found an interesting database. It is available from Kaggle. You can look at this. You can look at this later. So basically, it is for the classification of transcription, the clinical report, and for the medical specialty. So a clinical report is provided to you. The task is to classify which medical specialty this report corresponds to. Whether this corresponds to, for instance, to the Department of Oncology, to the emergency department, or to pathology department, or which department. Okay. So I'm going to load this data with this read data, and I'm dropping all of the places that I have not available value. Then I want to convert labels to an index. Okay, so the labels that I have, for instance, are allergy or immunology, which is or cardiovascular, dentistry, urology, or so on and so forth. Okay, so these labels need to be converted into a numerical format. So starting from 0 until whatever we have as the number of labels. So just that. Then I have my data. I have my pairs of labels, and I have the pairs of labels and the transcription. So the transcription and the medical specialty. This is my input sample, and this is my label that I'm trying to predict. I'm making an instance of pipeline. I only need to tokenize this. I don't need part of speech tags. I don't need the dependency relations. I only need to have the tokens. So I'm iterating over this data only for the first 200 samples. I will show you how this looks like. I'm getting the text. I'm passing the text through the pipeline. Then I'm iterating over the sentences and the tokens, and I'm getting these tokens. Okay. One thing that you need to pay attention here is to here I'm converting the token into its corresponding index. Here, if you look again, the corresponds to 0, a comma corresponds to 1, dot corresponds to 2, off to 3, so on and so forth. Okay, so instead of having a hospital as the input to a neural net, I'm passing an ID to the neural net. Okay, then I have this data processed. I'm converting these tokens and the label again to tensors. Now I'm ready to use this database. Let's run this. Now I'm ready to use this database, the data set for my classification task. Okay. So let's talk about CNN-based classification model. I have made a class. I made this class as a PyTorch module, a CNN for text classification. What are the actual components and the layers that I have in this model? I have an embedding layer. Embedding layer. It is initialized with the pre-trained embeddings that I have loaded in my embedding matrix. So I would have an embedding layer which I've loaded from my pre-trained model. Here I will talk about what does this freeze mean. Then I have a list of convolutional filters. I'm using conv1d. Why? Because I only have one channel. Okay, I don't have three channels like RGB images. I only have one channel. Okay. So then I'm having a module list of these convolutional filters. How many filters do I have, and what are the filter sizes? These are the hyperparameters that I would need to have as a part of training process during the training process. And then I also have a classifier. That basically classifies the output of this convolutional net for my classes. For how many classes do I have? In this case, I guess I have 39 classes because there are 39 specialties that we want to classify. And the forward. So what is the forward? What is the forward pass? The forward pass, basically you are passing the input IDs or the token IDs, the tokens that are converted to token IDs. You are passing this ID to the embedding layer. This embedding layer retrieves the corresponding embedding vectors or word embeddings for the corresponding positions of that embedding matrix. Then you are passing your input through this convolutional filters, and then, just like most of these convolutional nets, you're flattening your input, and then you're passing your input to a classifier. So in some sense, there's no difference between a classification using CNN for image or text. Okay. So I define a CNN-based classification model here, and then I'm making an object of this model. The filter sizes that I have is 1, 2, 3, and 4. So I'm interested in unigrams, okay, patterns, in bigram pattern, trigram, and 4-gram patterns, okay. And I'm setting the number of filters for each of these sizes to 30. So overall, I would have 120 convolutional filters. So then, just like always, I'm defining a loss function. There is a typo here, but nevertheless, loss function and optimizer. I'm iterating over the training data, and I'm doing the training. So I'm doing the training only for 200 of these samples. As you can see, the value of the loss, the average loss, is going down. I've trained this for 5 epochs. Okay, I can continue the training, for instance, for 10 epochs. Okay, here I'm continuing the training process for 10 epochs. You might need to adjust the learning rates. I just chose an arbitrary learning rate for this, but you can adjust the learning rate and do your classification and the evaluations. So practically, there was a reason that I chose CNN for text classification, because you were exposed to CNN before in the previous lectures. And I wanted to show you that you can treat textual input as an image and also classify it. So yes, this basically concludes my presentation. Any other questions? I would be happy to address your questions.
Thank you very much, Parsa. So yeah, right now the floor is open for questions. Feel free to put them on the chat or unmute and ask them directly. In the meantime, before I forget, there will be a tutorial hold next week on Thursday at 1:30 p.m. Montreal time. So again, if you have questions, feel free to put them on the chat or unmute.
Okay, this means that I either was very good or very bad. So thank you, Dr. Enger, for your message. It was a privilege. Thank you for giving me this opportunity to present as part of the MECMEDAC.
Well, thank you very much, Dr. Bagherzadeh. So we have a lot of thank yous on the chat. Maybe I can ask myself a question. Like you mentioned, you use like convolution 1D as your layer. Is there a way to use like conv 2D or 3D? Like let's
yes,
say
absolutely. Absolutely. So but the point is, you need to you also need you can also use conv 2D, but you need to set the dimensions of your input in a proper dimension, because conv 2D expects the input in a specific format. Okay, so yes, you can use conv 2D as well.
Okay, great.
So for instance, let me put it this way. Suppose an idea, for instance, that this idea, I have seen that this idea has been done in the literature, but for instance, you can have different channels for your text. One channel could be, for instance, global word embeddings. One channel could be word vectors, word-to-vec word embeddings, and so on and so forth. Okay, so just like you have different channels for color in image, you can have different channels for the representation.
I see. Okay, thank you very much. And overall, I think it was very complete, and so it was a lot of content for participants who may have not been aware of natural language processing before. So that might be why we don't have a lot of questions. But I'm sure if they go back through the content, they will come back with questions for this.
So the purpose and the way that I designed this presentation was my understanding was most of the participants they are new to yes, Dr. Enger is fantastic. She made a fantastic point. Yes, so they are new to neural nets and deep learning. They are new to image processing, let alone natural language processing. So while the purpose of MECMEDAC is mainly image processing, this was a break from image processing, a short break from image processing to have natural language processing. So the purpose is to basically also expose machine vision community or those who are working with medical images to also have some knowledge on natural language and textual processing. But for sure, I would talk about a little bit more about NLP and transformers, and next week when we got to talk about transformers, because we have a dedicated section for transformers.
Well, thank you very much. So I would like to congratulate you on this presentation and to thank you a lot in the name of all the participants, because that's a lot of work to come up with content tutorials for you guys. So thank you very much. And we're very much looking forward to see you next week for the next tutorial and enjoy a bit about transformers and NLP. So thank you very much, everyone, for attending. Thank you very much to our instructors and mentors that were here today. And feel free to connect to the tutorial next week on Thursday. And see you all next week for the seminars and tutorials and workshops. Thank you very much and have a great Sunday.
Yeah, have a good weekend. Bye.
Bye.